continuity of a lecture, but just try to come up with something like recording, try to come up with something like asking questions. Do not let teacher give you a prompt. I am raising thought-provoking questions to you. I have to make it in terms of the quizzes, but that's only for future. At present, I'll be asking questions, but you do also ask it. So what we have done, after having the basic introduction about the detection or the detectors, we directly came to something what we call as the gaseous detectors. Now, gaseous detector first requires what is called the ionizing particle, and as we discussed yesterday, charged and uncharged both are there. Once the ionizing particle ionizes, part of the energy also goes for the excitation. It is called the creation of the charges or electron ion pairs. It is also called ion pair. The next thing is about the migration of the carriers to the electrodes. This portion, which is called the collection, requires us to apply some electric field. The portion drift, which was not discussed yesterday, is about the drift of the electrons under the application of electric field. A small mention was there that we put electric field for the creation or for the collection. That portion takes care of the drift. The rest of the two components, thermal and diffusion, are what we discussed. Average charge creation is related with the average number of electron ion pairs, is related with the energy deposited in the detector divided by the average energy required to create electron hole pair. Average energy required to create electron hole pair is greater than the first ionization potential. Yeah? The word average is signifying that for a particular charged particle when it passes, it may or may not deposit exactly that energy. When we are saying that average energy required to create electron hole pair, it slightly varies from point to point depending upon how many interactions happen. What kind of interactions happen? Each interaction had the probability. While having the probability, how much energy was transferred to each of the electrons, having that probability. So make sure that you understand when I am using the word average, the instantaneous value may slightly differ from average value. But we do need to have some sort of quantitative analysis. So we are doing that quantitative analysis, that on an average we are going to see these many pairs, but there will be fluctuations about these pairs. How many fluctuations? When we will be dealing with our statistics class. Yeah, the probability and the statistics. Now, up to this we did, and then I said that I would like to come to something called mode of operation. So today's lecture is about that. Before coming to mode or modes of operation of gaseous detector, you already mentioned, so let me just write down. Current, pulse, mean square voltage, or we call it MSV, or we call it Campbell, something like that. But what we are going to do is to consider the current and the pulse right now. If the time permits, I will take up this MSV. I'll just give you a brief idea of that. Before that, before coming to the modes directly, what happens to this charge migration and collection when a single charge particle passes through my detector? So let's just take a detector, right? We will have some electric field, so the charge gets collected, and let's say a single charge particle has created charge. Now on an average, a single charge particle, how many charge will be created? Depends on what? So it depends upon what is the
delta E
energy which was deposited. Yeah. W on an average is almost all the time. If it is not given, you are going to use 30 electron volt because it varies from 22 to 41. So depending on this delta E, or the energy which this charge particle has, I will be having certain number of N naught, which will result in charge collected, right? So at this point, that means when this single charge particle went, then it creates what? Negative, positive. Negative will drift here, positive will drift towards the right, because there exists the electric field in the system. Yeah. So let's just make some current to close this. So at t equal to 0, Q is released. From what? Because of this passage of this wire. If the resolution of the current, if the response time of the current is of the order of microsecond, excellent picometer, if it is, then in that case, what are we expecting for this current? What has happened? Charge Q is released. Generally, the release time is of the order of nanoseconds. Yeah? But then charge starts migrating and will get collected into the respective electrode. So, when the charge gets migrated and collected in the electrode, most of the time you should see almost the steady current, because almost all the electrons are doing that. Some of the electrons, they were collected immediately, which were pretty close to this electrode, and some of the electrons which are at the far end, they may give you this kind of. We call this guy as TC. What is TC? TC we call the collection time. So time response of the emitter is of the order of charge. Now, so the emitter will show this kind of a beam if it responds to a single charge or a single particle passing through. Right? Now, from this curve, I am supposed to find out what was the charge deposited. How will I find it? So at t equal to 0, this pulse is started. At t is equal to Tc, all the charge is collected. In between, I get this curve, which is nothing but the current in the emitter. I am supposed to get charge from this because all I see is current in this meter. So how will I get converted into charge? Area under the curve. Excellent. So charge is nothing but basically saying that I can integrate it from 0 to Tc. Yeah. So a single instantaneous creation of charges get collected in collection time, and this is the typical kind of a curve which we are expecting if the response time of my picometer is of the order of the collection time. Yeah. All we need to see how this Q, which happens in a single event, if multiple charge particle comes, then how are we going to collect the charge? And that defines in which mode we are going to work. So this kind of system, when we are going to see, is only for one. If there are multiple, if the rate at which the charge particles are coming, let's say 1000 per second, we are going to see plenty of such curves here. Plenty of such. Current mode, pulse mode, or mean square voltage mode just tells you how am I going to record the signal out of it? That's it, nothing beyond that. Yeah. So let's start with something what we call as the current mode. And let's say R is the rate of irradiation or rate of interaction. In principle, it is correctly called rate of interaction, but for our class, okay. It is the rate at which we are sending our alpha particles, or photons, or beta particles, or any particles. Yeah. So generally, when R is the rate of the radiation, then we talk about not one pulse. This one pulse came because of one particle. Now there is a rate. That means that over the period of time, you will start seeing that one pulse is collected like this. Now another one does like this. Why? Because another pulse, for example, may have gone like this. In which case, they are pretty close to positive charge. So it will be collected very fast. And it gives this much of the big height. Another may be doing this. This is pulse to pulse variation. When I am saying average charge is released, it means I am basically averaging over very large. Yeah? But what is happening in the detector is something like these things. In fact, at this time itself you can say, sir, it is also possible that while the collection is taking place, another one also hits, and then what? Yeah. So at this time we are not complicating it beyond a certain. We can and we will be while we will be doing the daytime. But what happens in the current mode? That in general the response time. Remember, T capital T was response time of my picoammeter, the ones which it is there, or the ammeter. The response time here is of the order of 0.1 second, 0.01 second. We actually have plenty of these. In fact, now we are reaching to the point where the microsecond and the picosecond response time is also there. But when we talk about the current mode, we generally talk about the response time, which is much slower than the rate at which it is coming. So let's just give some numbers. So for example, let's say rate is 1000 per second. What does that mean? 1000 particles are hitting the detector per second. Yeah? So in 1 second, 1000 particles are hitting. If the response time is 0.1 second. So in that 0.1 second, how many charged particles have passed through? Thousands per second is the number at which it is hitting the my detector. Response time of this picoammeter, or the settling time in which it is going to respond, is 0.1 second, which means 100. 1000 multiplied by 0.1, 100 pulses or 100 of such charges have already gone through when my picoammeter is going to respond. It's called the settling time of the picoammeter, which means what I am going to see in my picoammeter in this current mode is what? What am I going to see? So if the picoammeter is there, with the response time which is 0.1 second, so T is 0.1, rate is 1000 per second. What am I going to see? I am going to see the total current which is flowing in the picoammeter equal to 1 over response time integrated over what? Okay, let's just do T minus T 2T I T prime dt prime. Let's look into it what we have done. This guy has given you one IT. This guy has given you another IT. This another IT. This another IT. So you have hundreds of this which have gone through my picometer. Picometer is going to give you the reading which is average of the reading or the instantaneous of that. So what happens? Hundreds averaged over. So this T minus capital T to T. How many I have basically averaged over? The ones which is 0.1 second. This much current is added together, divide by the response time, will be the current. This guy is for one particle, this guy is for 100 particles. Yeah. So our picometer in the current mode does give this one, which means that I do not care what is the exact nature of this guy. I do not care what is the exact nature of this guy. I only care in 100 such pulses what's the total current actually flow, and I just divide by it. So that is how a typical current meter works, and that is what happens in the current mode. So immediately it is clear to you that we lose any information related with individually. We do not have any idea of that because it has averaged over this. Now, what kind of nature this will have? The first result which you have seen is for first 100, right? If steady rate at which my particle keeps on coming. So what does that mean? 1000 per second I keep on hitting. How this current will respond? What kind of nature this current will be having? 100 first average, then next 100 has come, another average, next 100 has come, another average. What kind of nature we are expecting? So we have first 100 average, next 100 average, next 100 average, next 100 average. That's what we are expecting. Now, what kind of result will be?
Periodic.
So this result will be, so if we can think of IT as a function of t, not a small it, but capital IT. What's the difference? The response time is such that it is averaging over 100 pulses. This guy will start showing this kind of a behavior. Now what kind of behavior this is? At any given point, so first I can take mean of this guy and I will say there exists something called I naught, which is the average current. But the actual instantaneous current will have some variation with respect to the average, because every time you are seeing 100, not all those 100 have given you exactly the same charge. Because of the statistical fluctuation, each of these 100 averaging will give some variation with respect to the average one. So the result which you should be getting is some sort of I naught plus sigma IT. Now what is this sigma IT? This is instantaneous variation. For any given 100, I may or may not be seeing exactly the average. Yeah. Now let's just make this question a bit interesting. What if the response time would be 1 second, and what if the response time will be 0.01 second? What kind of curve am I expecting? So compare it with capital T is equal to 1 second and capital T is equal to 0.1 second. If you manage to compare these two, then you have understood what is happening in the system. So what do you think would be happening if I average over 100 as compared to response T is equal to 1 second? How many it is going to average over? Oh, in 1 second there are 1000 events. So I am now going to average over 1000 such charge. or the current. When response time is 0.01 second, I am going to average over only 10 such. What do you think is going to be seen in this? क्या आप लोगों को लगता है कुछ गड़बड़ हो मुझे तो इतनी दूर से दिख नहीं रहा कुछ वालों को बिल्कुल भी नहीं दिख रही होगी so let me just make something okay क्या होने जा रहा है भाई कुछ आइडिया right this sigma id is the one which will keep on changing if I am going to average over 1 second the variation the statistical fluctuation will start going down when you are averaging only over 10 pulses the sigma starts growing because your variation in 10 is far more than variation in 100 is far more than variation in 1000 so all what happens when we come up with the response time which is large is that we try to take care of these fluctuations in the current the average current remains same in almost all the cases now what will be the average current if I have to find out average current should be related with average charge which is created. But charge and current, there has to be some formula which should be relating it. So, what will be this I naught? What will be this I naught? Which is the average current? It should be related with average charge. We already know what is the average charge. So of course it has a term which is Q, which is basically equal to N naught E, which is basically equal to delta E over W times E. But current is not charge. It is charge per unit time. So what is the current, average current?
Capital T.
So this is nothing but multiplied by the rate. What was rate? 1000 particles were coming per second multiplied by the average charge created in each will give you average current flowing in the system. Now if you look into it, this formula does not have anywhere capital T. There is no capital T here. So average current is not going to change. It's the fluctuation over the average current which keeps on changing. So in some sense, this portion is a direct consequence of our study of statistical mechanics. So where statistical mechanics helps is understanding this one. That the fluctuations increase if the response time is less, fluctuations is smoothen out if the response time is more. Yeah. So current mode is generally used in this kind of a scenario. Now where will it become very important to do current mode? See, current mode loses information about any particular charge. It doesn't give you any information what happens to the amplitude of the first event, what happens to the timing, how much time did it take to cover that. Current information does not have because it is average. So current one mode is very important if there is a very high rate of interaction. And very high rate of interaction means these pulses are coming so fast that even if I try to get any time information from it, I cannot get it. Why? Because they are basically almost overlapping. And if they are overlapping, then there is no way I can actually extract any charge information, timing information, amplitude information from that. So when our current mode starts becoming important. The current mode starts becoming important when we have very high interaction. If it is very high, there is no way I am going to figure out what will happen in the individual pulses, as we will see in the pulse. Yeah? So it becomes where the place where it is used is called an ionization chamber, and we use it for the dose measurement. Where we are basically interested in something called that this is the steady state dose of what is coming. Now what is dose? Dose just tells you that how many charged particles are incident per unit time. Dose is related with figuring out the X-rays and the gamma rays. Okay, I am not going into that detail, but make sure you understand this. Two important points. First, you do not have information about the single pulse. There is no way, because we average out. 1. 2. This portion, which is the average current, this smoothes out if the response time is more, and this becomes larger if the response time is less. If the response time is more, basically what we are saying is, I won't be able to distinguish what happens in first 1 second, what happens in next 1 second. Because my current has smoothened out. I won't be able to say the fluctuation. Yeah? I will be able to say something that if a large change in the system has happened, that the rate is no longer steady state. It will start going down from average 1 to average next to average next to average next. But this is not the most important mode for our nuclear physics experiment, where we are interested in getting the information about the entire problem. The event which gets created as soon as a charged particle passes. Yeah? The one which I am not going to do is the mean square voltage. Mean square voltage deals with this sigma IT. Now since it is a statistical variation, so we do need to have some idea of the statistical variation, which means the standard deviation, how do we calculate those things. The reason why I am not doing it, because our mean square voltage depends completely on my standard deviation, which I haven't covered in this class. And this time I am not relying on whatever you have read back on. Because I have to do my probability statistics portion, there I will see if I can manage it. But as soon as you understand that mean square voltage will depend upon sigma IT, larger the fluctuations, better will be the mean square voltage. So it will go towards lower and lower time. But it will still be interested in finding out the fluctuations about the mean. So in that mode also, we do not try to see what happens to individual. Both the current mode and the mean square mode, we just look at the large time integration. And that's why in both of these modes, we do not manage to figure out the information about the single charge. Hence, we do not consider it till the rates become very, very high for us. If the rates are reasonable, then we change to our mode, which we call as the pulse mode, in which we are interested in getting the information about this. So questions at this point for the current mode, so that I can just come to the more important mode for us, which is the pulse mode.